Well, welcome back. We are now going to be talking about the second form of electricity, where previously we talked about static. Hopefully you didn't shock any of your siblings. Uh, we're going to be talking about current electricity now. And this one we're going to be spending a lot more time on over the next couple of weeks, and it's actually a pretty usable one for us, and you're going to notice there's lots of cool applications for it. So we're going to start off by talking about one of my favorite things, rivers. So let's describe this river. And Miss Engelhardt has been volunteered to describe the river for us. So Miss Engelhardt, what are some things that you notice when looking at this river? Or things that you'd want to know about the river to describe it?
Okay, well, it looks like a fairly wide river because you can tell the little people are pretty small, so it's a pretty wide river.
Yeah.
Um, there's some areas that look like they're a deeper blue, so they might be deeper, like a lot more water in them, and others that are lighter that might be a bit more shallower.
Mhm.
Um, the white there tells me that there's probably rapids, so the water's probably moving a bit faster in that narrow part there than
Right.
it is in the even wider parts
Mhm.
because it has those white waves there. Yep, then it looks like it like bends and turns quite a bit too.
So you're saying that the things that you, when you're looking at a river, is you want to know,
Like the
um,
speed of the river, how
yeah,
deep it is.
how deep it is, how much water, any sort of curves or twists, right?
Yeah.
Um, I mean, if I'm going
I'm
around this corner, I would really want to know if there's a waterfall on the other side.
yeah. Or if you're trying to get to the other side, how far it is to swim across.
Right. So like here would be shorter to go across, but probably more dangerous because the water's faster. Here might
Yeah.
be wider, but the water's probably a bit
A bit slower, might be easier
slower.
to swim across.
Yeah. Okay. Cool.
Not
Yeah.
heading towards the waterfall as fast.
You have time to like scream for help, and hopefully
Yeah.
the Baywatch people come and get you. Yeah. Yeah. So those are all pretty good descriptions. And why is it we're describing a river? Well, when water is going through a river, we say that it flows, right? But that's actually the same terminology we use for electricity with current electricity. When we think of a river, we have a current. And when we think of electricity, we have a current. So let's look at how that works here. So there's our little river. So what we needed to know in the river, and let's just apply it to electricity here, was how fast is the water? Now with electricity, we could think of electricity as moving fast, um, but really, it's like when something moves fast, it hits you harder, right? Like if if I threw a water balloon at you and just kind of chucked it lightly at you, it's not going to hurt you. But if I wound up and threw it as a fastball, it could hurt you. The speed matters, right? So when we're talking about electricity, it's there. How much water is there? Of course, that's important to know. And with electricity, we'd want to know how much electricity there is, right? And then we'd also want to know if there's any bends, curves, or narrow or wide sections, waterfalls, anything that kind of disrupts the current there. So let's take a look how this applies to electricity. Um, there we go. So uh, when we talk about how fast water is, okay. Now I put up the picture of the garden hose just because I want to show you that. Have you ever done that in the backyard? Create your own power washer?
Hmm.
Your own pressure washer? Yeah. I actually had to do that the other day. My garden hose wasn't quite long enough to reach the back of my garden to water it. Um, and so I put my finger over the end and I was able to kind of shoot the water a little bit further, but then it was coming out really fast. So I had to kind of arc it up in the air so it didn't like tear the leaves off my tomato plants. But,
I've done that so that to clean the bird poop off windows.
oh, there you go. Yeah, that works too. Now, when you put your thumb over it, what happens to your thumb?
You can feel the pressure on it.
Yeah, it's
Like you have
pushing
to
it,
really
right?
hold your thumb there. Yeah.
But would we agree that we have the same amount of water coming out of it? Yeah, right. It's the
Yeah.
same amount of water
Yeah.
coming out. You're just taking, instead of it having like a wider kind of dribble, it has a thinner kind of faster flow, right? Okay, so again, let's just think about these in terms of electricity. Um, so when we describe how fast or hard the electricity is, we're going to use what's called voltage. And the units is volts, symbol V, okay, V and V. And then how much electricity? We use the word current. So it's the current. The unit is amperes or amps, which is A, but the symbol for current is I. And remember that. A is just on the units for amps, but I is actually symbolizing current. And then how much the flow of the electricity is being fought. So think of like the water pushing your finger off of the tip of the hose.
And you fighting to keep it there.
Yeah, exactly. And you fighting to keep there. Well, that's resistance. This is the resistance to the flow. And we'll talk about how volts kind of factors in that in a second here, but it's a resistance. The unit of that one is ohms, after the, I believe it's a German scientist that kind of just created the law to describe resistance, unsurprisingly known as Ohm's law, which we'll talk about in a second. The next slide, I think. And the symbol for that is this, and that's just the Greek letter for sigma. Is it sigma? Yeah, sigma. I think so.
Yep.
So there we go. That's ohms. It just kind of looks
Kind
like
of looks like the God of War symbol if you play video games.
Yeah, there we go. Exactly. Yep. Or like a upside down horseshoe. Okay. And here's a picture. A picture paints 1,000 words, right? So the amps is the actual columns of electricity. Right? The columns of electricity is the amps, and we're trying to push it down. I mean, in this case, it could be a wire or a tube. And what's pushing the amps? Well, that's the volts. The volts is how hard we're pushing. So we have the electricity, the amount of electricity, which is the amps. We have how hard we're pushing it, which is the volts. So he's trying to push it into the hole. And then we have this little ohm sheriff guy, which is causing the resistance. They're squeezing it to kind of slow down how fast the volts can push the amps. Right? And that's electricity, right? You have these three kind of competing factors. You have how much is trying to flow, how hard is being pushed, and if you push something hard and there's no resistance, it goes quite fast, right? So you can think of speed, but really what we're talking about is how hard the water is being pushed or how hard the electricity is being pushed. And then ohms is just the resistance, the what's slowing it down, making it so it just doesn't shoot out, you know. And these are really the three things you need to know about current electricity in terms of like describing it. It's, you know, how hard / fast, how many, and how much are we stopping it. Okay. So what that comes down to is what we call Ohm's law. And there's a relationship between the volts and the current. Now, you've heard of Ohm's law. Ms. Engelhardt, have you ever heard of Cole's law?
No.
No? It's a little bit of cabbage chopped up with some mayonnaise. And get a coleslaw. Got you with one. Okay, so there's a relationship between volts and current. So if I was to graph it, the ratio of volts per current equals resistance. So here's a graph. I have volts and I have current, and when I graph it, it makes a straight line, and that line is resistance. The slope of that curve is resistance. It's the ratio of volts to current. That's what it is. That's how the three of them fit together. Okay? And you've seen this before, talking about mass and volume and density. Right? Density is just a ratio of volume to mass, or well, mass to volume rather, mass to volume. Right? So it's the same sort of idea. What that looks like is we have the volts divided by the current equals resistance, this nice little triangle. Now using some algebra, we can rearrange for I. Well, basically you're just multiplying both sides by I and then dividing both sides by R, blah, blah, blah. But what you find out is you can just switch the I and the R, right? You just cross multiply and switch them. And we end up with, take the volts divided by resistance, you end up with the current. So there we go. But how can we figure out what resistance is? Well, I'll throw up a definition of resistance, which is Ohm's law states that volts, how fast, is a product of how many electrons, current, combined with the impediment, or resistance to the flow. Now that's a whole mouthful, but what we're saying is that volts is equal to I, current, times resistance. So how many electrons multiplied by the resistance is how hard they're pushing. Now, if I take all three of these, I can put them together and get my classic triangle. Okay. Now, on class on Monday, we're going to be having a live session where we are going to be going through some math and word problems with this situation. So there'll be more to come on this. If you're going to look in the folder and see some questions pop up on Monday, don't panic, because we're going to actually go through some instructions on that. But it's all similar to the stuff that we did on density. And you just have to know that anytime you cover one of these, you get how to rearrange for the other ones. And we'll cover that later. So that's how volts, current, and resistance are related. Is this nice little triangle. Now the last thing we want to mention before we get off of series is, or not series, current and electricity rather, is one other key idea. Is that how do we move electricity? Well, it all goes back to one of those properties of matter, which was ductility. We use wires. You know, there's some metals that we can turn into nice thin wires. What were some of those metals that we talked about? Do you remember?
Copper,
Yeah,
aluminum,
yeah, gold, I guess.
gold.
I think silver is actually the best one, but it's too expensive to use in all the house, like to use in your house. I mean, your house would be worth like millions of dollars of just like wiring if we use silver. But I want to say silver is one of, if not the best, but platinum, palladium, those are all really good too. But we use copper because it works pretty good and it's pretty cheap in comparison, right? But it's ductile. We can turn it into wires, flexible but strong wires. Now, what a wire looks like is this. You can have these little copper spindles. If somebody reminds me, I'll explain why we actually have multiple small wires rather than one thick wire. Okay? And we'll discover that when we get into different circuit types, actually. But you have a wire in the middle, and then you have this stuff on the outside. So there's two key concepts we want here, which is one, conductors. They lets the electricity flow, and that's the copper part. The electricity can flow up and down the copper. It's happy to let electricity pass by. The electrons can kind of bounce from atom to atom, bounce from copper molecule to copper molecule, and just go down the wire. Okay. But we want the electricity going in the direction of the wire, so like if we just had this wire here, the electricity can kind of go off of it in any direction it wants. Well, we solve that by insulating it. Okay, so there's your conductor, but then what we do is we coat it in something that's an insulator, something that stops electrical flowing. You know, stuff like rubber, wood's a very good insulator. Air is an amazing insulator. Plastic, right? These are all good insulators. And so we coat the rubber wire or the copper wire in some rubber or plastic, and it becomes an insulator. And that's what most wires are made out of. So we have these insulators and conductors. Okay. Any questions, comments, anything you want to add to this?
No, I think we're pretty good.
We're pretty good. So
Yeah.
what they got to remember and what's going to be important for their work is this little triangle. So tune in on Monday, and we'll be going through some of these questions on how to solve Ohm's law. So that's bye for now, and if you have any questions, like always, ask.
Yeah. Have a good day.